Hi everyone, I'm Sonia Minsuk Kim from Stanford Electrical Engineering. Today I'll present dual Ascent diffusion for inverse problems, joint work with Axel Levy and Gordon Wettstein. Many imaging tasks like deblurring, in-painting, and phase retrieval are inverse problems where we recover a signal from indirect observations. They are ill-posed, so a strong prior is essential. Existing diffusion solvers fall into two camps. Posterior samplers like DPS and DAPS couple the prior and data feed updates inside the reverse diffusion, but they require score model backpropagation or inner MCMC. Half-quadratic splitting-based map methods like Diffpir and DCDP decouple the two updates, but they have no mechanism to correct constraint violations across iterations. We propose dual Ascent diffusion, or DDiff, which tightly couples a diffusion prior with principled data consistency updates across diverse inverse problems. We start from the standard map objective: minimize the negative log likelihood plus the negative log prior. Under Gaussian measurement noise, this becomes a quadratic data fit plus log p of x. We split it with ADMM by introducing a slack variable z and a scaled dual variable u. This gives 3 updates per iteration. The x update enforces measurement consistency, the z update applies the prior, and u accumulates the constraint violation x minus z. A naive plug-and-play approach uses a pre-trained diffusion denoiser for the z update via Tweedy's formula, replacing the prior step with a single denoising pass. But this naive approach breaks. The score function S theta is only reliable on the diffusion manifold at noise level t. The point x plus u lies off that manifold, so the denoiser output becomes unreliable. As iterations proceed, high-frequency artifacts appear and accumulate, and the reconstruction degrades. DDiff keeps the ADMM dual Ascent structure but replaces the naive Z update with a DDIM-style reverse diffusion step that stays on the manifold with the dual variable folded back in at the correct signal scale. As t decreases, the primals x and z progressively align and u shrinks towards 0. You can see this in the figure where u fades out as we denoise. We also prove it. Under bounded denoiser and bounded gradient assumptions, the iterates form a Cauchy sequence and converge to a fixed point of the form x star 0. No convexity required, and to our knowledge, this is the first fixed point convergence result for diffusion-based posterior optimization. Two design choices act together here. First, U accumulates the constraint violation x minus z across iterations, so measurement consistency is enforced over the full trajectory. This is what HQS methods lack. Second, the noising step stochastically pushes the iterate back onto the diffusion manifold at the next level, keeping the score model accurate throughout. Ablations show that removing either component degrades performance. We also introduce latent DDiff, which applies the same structure in the latent space, giving lower memory and compute while retaining data consistency. We evaluate on FFHQ and ImageNet 256 100 validation images each with measurement noise standard deviation sigma of 0.05. We cover 5 linear tasks including super resolution and in-painting, and 3 nonlinear tasks including phase retrieval and high dynamic range. DDiff consistently achieves the best or second best PSNR, SSIM, and LPIPs, and the lowest measurement residual. The residual metric shown here measures data fidelity and is further discussed in the appendix. The qualitative comparison on the right shows sharper reconstructions with fewer artifacts than DPS or DAPS. Please see the paper for the full set of results. DDiff is also robust to high measurement noise. On the left, we show PSNR and LPIPs on phase retrieval as we sweep sigma from 0 to 0.3. DAPS degrades sharply while DDiff stays stable. There are 2 reasons. First, at high sigma, the posterior broadens. DDiff returns a near map point estimate, while DAPS inherits the variance of the broadened posterior. Second, U absorbs per-step gradient noise across iterations instead of propagating it forward. On the right, we show the runtime on Gaussian deblurring. Our method reaches better LPIPs in less compute time for the same given number of neural function evaluation. To summarize, DDiff is an ADMM-inspired diffusion solver for inverse problems. It delivers higher image quality across multiple metrics, robustness to high measurement noise, lower measurement residual, faster sampling, compatibility with latent diffusion, and provable convergence under mild assumptions. Thank you very much for listening. Feel free to reach out at kminsa@stanford.edu and come find our poster at CVPR.